Welcome, everyone. Thank you for joining today's session on the evolution of our technical infrastructure. What you see on the screen is the Modern Platform Framework, which serves as our definitive blueprint for architectural standards involving Kubernetes, Istio, and event hubs. This diagram illustrates our platform engineering guidelines, specifically Architecture version 2.0. The concentric rings visually represent the core layers of our ecosystem, with the precisely defined measurements indicating the specific scope and integration boundaries for each component. By adhering to these standards, we ensure a unified, scalable, and resilient foundation that enables our development teams to deliver high-quality services with maximum consistency. Historically, we categorize our digital infrastructure through a binary lens, public versus internal. This old model focused almost exclusively on network surface area. However, as our systems have evolved, this simplistic view has become inadequate for ensuring system robustness. We are shifting toward a new model that recognizes the multidimensional nature of modern applications. Instead of just looking at network access, we now categorize applications based on three primary axes. Along one axis, we define the runtime stack, differentiating between virtual machines, containerized environments, and serverless architectures. Along the second axis, we identify 5 distinct workload archetypes: edge, transactional, analytical, streaming, and batch. These are then layered across the core functional components of networking, data, logic, and compute. By embracing this more granular categorization of workload behavior and runtime characteristics, we can build ecosystems that are far more resilient and better aligned with the complexities of modern cloud-native environments. To visualize our ecosystem, we utilize a tiered architecture represented by these concentric circles, moving from the external-facing edge to the secure internal core. The outermost layer is the public or edge zone, which serves as the primary entry point for internet-facing traffic. This layer hosts our API management and Category 1 public web applications. We employ Istio Ingress here as a Kubernetes native ingress controller to manage service mesh traffic and security at the perimeter. The middle layer is the DMZ or ingestion zone, acting as a secure buffer for internal administrative consoles and event processing. In this tier, we utilize event hubs as a scalable data streaming platform and event ingestion service to handle high-volume data before it transitions to the core systems. At the center lies the private or core zone, the most secure area of our environment. This layer contains our Category 2 internal APIs, Category 3 worker services, and primary databases. We use Kata within this core zone to provide Kubernetes-based event-driven autoscaling, ensuring our most critical workloads scale efficiently in response to system demand. This layered strategy provides a clear separation of concerns, balancing accessibility with rigorous security controls. Our workload framework for HTTP and traffic services is divided into 2 primary categories, based on how the services are exposed and how traffic is managed. Category 1 is the edge service. These are applications directly exposed to the internet, meaning they handle high traffic volumes and require robust DDoS protection. The technical stack for these services includes standard Kubernetes deployments paired with an Istio Ingress gateway. We manage these via an API management layer for precise rate limiting. A common example here is the BFF, or backend for frontend, which aggregates data for public-facing apps and handles routing through Istio. Category 2 is the mesh service. These represent internal microservices that only communicate with other services within the cluster and are never directly exposed to external traffic. Their stack consists of deployments and cluster IP services. A key feature of the mesh service is its reliance on Istio sidecars. This allows us to enforce mutual TLS for internal security and implement automatic retries to ensure service reliability across the mesh. Moving into the second part of our workload framework, we focus on asynchronous processing and state management. Category 3 represents the event worker. These applications do not serve HTTP traffic. Instead, they listen to event streams, like event hubs, process the incoming data, and write results to a database. Technically, these are Kubernetes deployments integrated with Kata, which allows them to scale based on message lag or queue depth, rather than traditional metrics like CPU. Category 4 covers the batch job. These workloads are designed for specific tasks, like generating reports, data reconciliation, or nightly cleanups. They operate on a run-once-and-die principle. We implement these using Kubernetes cron jobs, which utilize transient pods that do not require open ports. Finally, Category 5 is the stateful app. This category is typically for legacy applications that require local disk persistence or sticky sessions. To support these needs, we use Kubernetes stateful sets paired with persistent volume claims. Additionally, we leverage Istio to handle session affinity, ensuring that traffic from a specific user is consistently routed to the same pod. The Placement Strategy Decision Matrix outlines the workflow for an incoming application request as it navigates through our architectural layers. The process begins at Phase 1, the Istio layer, where we determine the specific connectivity requirements. If the request originates from an external source, it is routed through APIM and the Istio ingress. For internal UI requests, the flow is directed toward ingress with OIDC authentication. When a request requires back-end logic, it transitions into Phase 2, the event layer. Here, the decision is based on the communication pattern required for the task. Synchronous or blocking requests are handled using REST or gRPC protocols. Conversely, for asynchronous or fire and forget operations, the request is routed through event hubs to a Category 3 worker. This matrix ensures that every request is processed using the most efficient and secure communication path based on its specific functional needs. The Runtime Stack framework provides a methodology for standardizing our infrastructure by resource profile rather than just by programming language. This approach categorizes workloads into 3 distinct stacks, each requiring a tailored resource strategy to ensure optimal performance. The JVM stack, which includes Java, Kotlin, and Scala, is characterized by a high memory footprint and relatively slow startup times. Managing these applications requires heavy memory tuning and often utilizes init containers to manage resource allocation effectively during the startup phase. In contrast, the native stack, comprising Go, Rust, and C++, offers a tiny footprint and near-instant startup. This profile allows for the use of distroless images and supports aggressive autoscaling, making these applications highly responsive to immediate changes in demand. Finally, the dynamic stack covers Node.js, Python, and Ruby. These environments are often single-threaded and highly sensitive to CPU availability. When managing these workloads, we prioritize horizontal scaling over vertical resizing to maintain stability and performance. When operationalizing runtimes, we must distinguish between the specific needs of JVM-based systems and dynamic environments like Node.js or Python. For the JVM strategy, commonly used with Java and Spring, a recurring challenge is the cold start, which frequently triggers Istio timeouts. To mitigate this, we first set the max RAM percentage in the Docker entry point to ensure the JVM correctly understands its containerized memory constraints. Additionally, we configured generous startup probes, typically ranging from 60 to 90 seconds, to allow the application sufficient time to bootstrap before it is marked as ready. Regarding observability, Java agents are highly effective here, as they automatically inject B3 headers for distributed tracing. Conversely, the dynamic strategy used for Node and Python faces challenges related to single-threaded architectures where blocking requests can halt processing. Our primary fix is to mandate a minimum of 2 replicas, ensuring we never run a single instance so that availability is maintained. This makes horizontal scaling a top operational priority. Unlike the automated approach of the JVM, tracing in these environments usually requires manual header propagation for fields like xRequestID to ensure end-to-end visibility. When operationalizing runtimes within a native stack, we encounter a specific startup challenge illustrated here. Native applications, such as those compiled as Go binaries, boast incredibly fast boot times. However, this speed often creates a race condition with a network sidecar, such as an Istio proxy. As shown in the timeline, the application attempts to establish network connections almost immediately at t=0. Because the sidecar proxy takes longer to initialize and become ready, often not reaching a functional state until several seconds later, the application's initial connection attempts fail. This mismatch frequently leads to immediate crashes and repetitive crash loops. To mitigate this risk, we utilize a specific configuration fix by setting hold application until proxy starts to true. This ensures the container lifecycle is managed correctly, delaying the application's startup sequence until the network plumbing is fully operational. Finally, for the most secure and efficient native deployments, we recommend using distroless or scratch-based images, though it is important to remember that this approach requires binary rebuilds whenever OS-level patching is necessary. Our governance, security, and data layers are structured as a unified compliance stack to ensure every application adheres to our organizational standards. Starting at the foundational level, Layer 3 focuses on build automation. We utilize cloud-native build packs for auto-detection, which removes the need for custom Docker files. This automation ensures that builds are consistent, secure, and free from manual configuration errors. Layer 2 addresses our base images. We rely exclusively on a trusted registry populated with hardened images. Our governance model dictates strict parameters for choosing between Alpine and Debian environments, ensuring that every container starts from a secure and minimal baseline. Finally, Layer 1 manages data sensitivity. For Tier 1 workloads handling PII or financial data, we enforce rigorous requirements including strict mutual TLS and egress deny policies. This layered framework provides a robust defense-in-depth strategy, automating security from the build phase through to runtime data protection. Let's walk through a practical integration scenario for the intake flow. It begins with a standard developer request, in this case for a Python API intended for internal use. This request is categorized by the platform as a mesh service, specifically Category 2, running on a dynamic stack runtime. By combining the developer's intent with these workload classifications, the system automatically produces what we call the golden path config. This configuration defines all the necessary operational parameters. The network is restricted to cluster IP only, security is enforced through Istio MTLS strict mode, and resources are optimized for high CPU and low memory usage. Additionally, it sets a minimum of 2 replicas for scaling and incorporates a Python header wrapper into the code. This process ensures that every service follows organizational best practices and security standards from the moment it is provisioned. To ensure every application is production-ready, we follow this platform checklist as a foundational guide for architecture and deployment. First, we categorize the intake based on workload behavior, distinguishing between edge, mesh, and worker profiles. This classification determines how a service interacts with the network and its specific discovery requirements. Next, we select the runtime stack, choosing between JVM, native, or dynamic environments. This selection is vital for establishing precise resource limits, allowing us to tune memory and CPU usage effectively for each specific technology. For background processing, we focus on decoupling components using event hubs and Kata. This worker profile enables event-driven autoscaling, ensuring that our infrastructure reacts dynamically to message volume rather than just traditional metrics. Finally, we enforce governance by mandating hardened base images, consistent header propagation for observability, and MTLS for secure, authenticated communication between services. By adopting this golden path, we provide a standardized, repeatable framework that bakes reliability and security into the core of every deployment.